Thanks. I'll start off. I'm going to beg your forbearance before I get going. I've got a really rotten cold here, so I hope my voice will last for 45 minutes. I've got my water, my ginger ale, and my Halls here. And frankly, most people wouldn't consider me losing my voice necessarily a bad thing. Yeah, I'm going to talk about the survey we did over the Lalor Lake deposit with a number of digressions in here for some sort of side issues that are, I think, of interest related to the work that we did there. So this is the Lalor Lake deposit near Snow Lake in Manitoba. You can see it there, a few hundred meters in size, well, about 8 by 500 meters. Was originally found with ground EM. Big anomaly there. They used sort of a supercharged ground EM system to find it. Found that, and also found one that so far all I can find for all that Hudbay will give me for name is they call it the South Bullseye. So we've got this other conductor as well, and we flew over both of them. We'll be testing both of them. This is what it looks like. There's multiple zones there. You can see in the section in the bottom right how they're stacked one on top of the other and sort of feathered out a little bit. In the order of 900 by 700 meters, most of them. They're about 570 meters to the top, and they dip to the north and northeast, as you can see there. Fairly shallow dipping. From Hudbay's report there, coarse-grained pyrite sphalerite underlain by thick zone of intense hydrothermal alteration, varying concentration of pyrite, pyrrhotite, copper. Lots of conductors there, but also lots of stuff that's kind of hard to characterize. We've got the flat slab conductors, but we've got lots of alteration and stockwork underneath them. But certainly lots of conductivity. The other thing you always have to look at is what's on top of it. Rock units, the hanging wall, felsic volcanics, mafics, fragmental tuffs, a lot of things. Most important thing, fairly resistive stuff on top of it, so not real hard to see through, which is good. We've got a long way down to go. So we wanted to try it. It's a tough target because it's pretty deep. I like to say if it's as big as it is deep, then you've got a chance, and this thing's only as big as it is deep, not much bigger. So it was found with the extra large ground EM. Wasn't detected previously with airborne time domain EM, so we wanted to try it as a proof of the system. A lot of questions we had to ask about how we would go and see it, like power and base frequency. And we had quite a number of options. Power, well, of course, you want as much power as you can get. But there's always a trade-off in your power with your pulse width and the frequency you're transmitting. Those are going to affect how much power you can put out. The base frequency, 30 hertz is most common. An obvious thing when you're trying to go deep for strong conductors is to go to a lower frequency, like 15 hertz. But 15 hertz, you're stacking half as many samples as you're at 30 hertz, so it's going to increase the noise somewhat. The pulse width, well, we could do any one of these, 4, 6, 8, or 10 milliseconds. You get more low-frequency content in your pulse if you go with a wider pulse, but then you lose off time after that pulse to see the decay curve. And the processing, what are you going to do in the field? What are you going to do for advanced processing, and where are you going to take it? So this is true of all EM-type work. There's almost always a trade-off. It's not real simple to say, oh, we can do this and we'll get better results. You're always trading one against the other. So the first thing to do is model it. Before I get into that, I'll get my first digression here and talk about geobandwidth, which is something we've defined to define the response spectrum of the system, including the Earth response, by the response to a range of wire loop conductors. People like to look at transmitter waveforms. Liu did it. Engineers like to look at the power spectrum, but that doesn't include the Earth response. So we like to build that in by using a series of wire loop conductors. Fairly easy math, too. It's easy to implement. I do it in a spreadsheet. But what we're looking at in a curve like this is the response on the y-axis to a range of conductors, from very weak conductors on the left to very strong conductors on the right. You can see where the decay curve would be for any particular conductor. And so you plot the response for each channel for the full range of decay constant, tau. And you can do it in nanotests per second or picotests or whatever your heart desires. You can compare systems by using signal to noise even. So this is the response spectrum of the geobandwidth of a 6 millisecond half-sine pulse. If I overlay that on a 4 millisecond half-sine pulse to compare them, it gets to be quite a mess. So what I typically do is just look at the first and the last channels that we're using. So here the 4 milliseconds in dashed line and 6 milliseconds is solid line. And this is the range of of decay constant or tau that we might expect for Lalor Lake based on what we've seen in the other data. So this is the sort of spot where we want to look at. We can see the whole range here, but we focus most on that. And the first thing you see here, if you look at the high frequency or the early time, we shift a little bit to a more conductive and lost some signal right in here for these weaker conductors by going to 6 milliseconds, which is about what we expect. We have less high frequency in our waveform. We've also lost a little bit of the late time bandwidth here because we have less off time. But we have more low frequency energy in our pulse. So we actually have more energy into strong conductors, even though we've lost, in theory, a tiny bit of bandwidth. And you can see in our range of interest, there's definitely an increase in the amount of signal you're getting using 6 millisecond pulse. Also wanted to look at the 15 hertz option, and for that we were considering a 10 millisecond pulse, so that's what the waveform looks like. Looking at the first and last channels again, compared to a 30 hertz 4 millisecond, and you can see, again, lots of lost bandwidth for the weak conductors, but we don't care much about that in this case. Got more bandwidth. You can see it extends further into the strong conductors, the long tau conductors, but not a whole lot more bandwidth in that area we're interested in. We're not at the very strongest end of the conductors, but somewhere in the middle there. So a modest advantage, perhaps not huge. Yeah, there's the two waveforms overlaid. So here we're looking at 6 milliseconds 30 hertz versus 10 milliseconds 15. These are the two we ended up deciding on. And what I've done is overlaid just a few of the 6 millisecond channels on top of there. Because you've got to remember, we can't match channel to channel in something like this, because 6 millisecond pulse, we have less time than we would with 15 hertz. So you don't want to compare channel to channel. What you want to compare is your best channel from each method of doing it to see which one's going to give you the best result. And that's what we see here. 30 hertz is better for weak conductors. Well, we kind of knew that. 15 hertz, the later channels, don't give a whole lot of advantage in detection because they're lower signal. But it does give more in that range here, the 10 millisecond pulse. You've got a little more signal. You look at the brown line there. It's got a little more signal in there. But the later channels are much lower signal. So you do have some in that mid-range of the 15 hertz. If you looked at the last and the last, it wouldn't look as good. So then we wanted to actually get out there and model the thing. This gave us an idea. So we've settled on those two frequency pulse combinations. So the size estimated from the drawing, about 800 by 500 meters, about 550 meters depth, 1 meter depth. And from the ground geophysics, we knew we had about a 15 millisecond decay constant, so that's about a 200 Siemens conductor. And there's the systems we tried. Well, I tried a whole range of different ones here. But basically, at 30 hertz, the off time, you got a 16.6 milliseconds minus whatever pulse width you use, as opposed to 30 milliseconds minus pulse widths for the 15 hertz. And that's what it looks like. I can't remember why I used 2.5 million amp meters square. We normally can only get about 2 million amp meters square, but a 6 millisecond pulse. The lowermost channel there is the 10 microseconds, so our first off time channel using the axis on the right. Lots of signal. Important to note, there is still definitely lots of signal from this strong conductor at depth, even the earliest channel. I'll talk about that a bit more later. By channel 9 out at 250 microseconds, you can see we've got about 7 or 8 picoteslas in the B field, so not a whole lot of signal for that. If we had really pessimistic noise taken from another older survey, it's pretty hard to pick that out of there. It's there. You can see it if you know it's there, but you wouldn't pick that out. Going with a 10 millisecond pulse, so now we've got more energy, and you can see, if you look at the difference in scale, there's less background signal in the 10 or in the 15 hertz data, and more signal from the strong conductor. So that's what we saw in the geobandwidth as well. And a lot less, even on the right there, the circles show you there's a lot less signal in the earliest time, but that's what we would expect. Add a whole lot of noise to that again, the same sort of noise, and the conductor's there and it's stronger now than it was, but it's still quite weak. So this was not really encouraging. Well, before I go on though, to actually doing it, I want to talk about another misconception And that is, you very often hear people say, basically, you got to look at the latest time for the deepest conductor. If you're looking deep, you look late. Pure and simple, works really nice. That's true in conductive ground, because what happens, of course, the currents start flowing near surface, they propagate deeper and deeper, and only once they get deep enough do the currents start to channel along the conductor and give you a good response in the conductor. That's the galvanic energy getting into the conductor. So that's what happens in resistive ground. Sorry, that's what happens in conductive ground. You've got to wait for late time. And that's how we come up with charts, something like this. It's just looking at the fraction of the skin depth, and we say this is our effective depth of exploration. But you got to remember, in a place like Snow Lake, you're dealing up here in 5,000 ohm meters or higher. And so even your earliest channels are already down to the depth of that conductor. The current ring is moving down incredibly fast. And so what you get is the current ring's gone almost by the first few channels. It's gone down deep very quickly, but you've induced current in the conductor from the EM field. There's not as much galvanic energy getting into the conductor. And those decays are going to start very early and stay in the conductor until late time. And every conductor in the world, the response decays, which means the response is still biggest in the earliest time. So the earliest channel you can see the thing is where you want to start looking. You don't want to wait till late time when it's already starting to decay away. So we'll see that when we get some of these data. I modeled channel 9, which is 250 microseconds. It's pretty early time, and that was about the strongest channel that we had on Lalor Lake for amplitude. So the models indicated it wasn't worth doing. That was my opinion. Fortunately, management decided to do it anyways. 15 hertz, as you saw, was a little better, but not really significantly better. 10 milliseconds, a little better as well, except you lose signal in the stacking. So we decided to try that anyways. So we went with 30 hertz with a 6 millisecond pulse as our best option, but we also tried the 15 hertz. We carried out the tests in 2012 there between Lalor Lake and Chisel Lake. 30 hertz initial test. We flew over a test line back and forth over to see what we got, and then went on to fly the entire area. And it was a pretty low amplitude, long wavelength anomaly, just a few picoteslas, a few kilometers long because of the depth. So there's the system, 708 meters squared transmitter, 900 amp peak current, and about 1.9 million amp meters squared. And that's what we flew over it. So that's where Lalor Lake is, and what's called Chisel Lake there, that's basically where that the south bullseye anomaly is. Chisel Lake itself is right at the bottom edge. And I'm really simple. I like to see my results in field data. I mean, inversions are great. You enhance it, you get much better results. But if I see it in inversion, I don't see it in the field data or in at least fairly basic data, it makes me a little nervous because inversions can do wondrously amazing things. And so this is the field data. This is very raw data. And you can see definitely a broad high as you go over the Lalor Lake deposit. If you look at it in differential conductivity section, it's even more obvious in there that you've got a broad high. We've also got that graphitic conductor up to the north end. Third digression, I promise it's my last one, is the differential conductivity. I've talked about it, and I think the last time I talked about this, somebody said, what is this differential conductivity? Something that was developed years ago at Digression by Doug Fraser and Haoping Huang. Calculate the homogeneous half space for every frequency with a frequency domain EM system. That's fairly commonly done. But we know each lower frequency is sampling a greater volume of ground. It's sampling deeper. So we can take the high frequency sampling near surface and use that to correct our bigger sample, our deeper sample, for what's going on near surface, and basically refine our knowledge of the deeper layers by sort of removing the effect of the shallower layers. And just as that applies in frequency, it applies in time domain EM. Well, you just replace high frequency with early time and low frequency with late time, and you get the same sort of conclusion. We use it because it's really fast, it's very easy to do, it's robust, you can do conductivity or resistivity, whatever you choose. It's surprisingly accurate. We do have important clients in frequency domain who that's all they want from us because it works well, it's quite robust, it's not model dependent, so you don't have to worry about that. And we like it now because we've developed it in time domain. It's quite compatible between the two methods, so we can merge time and frequency domain data basically right off the field data. So here's the B field, and we're going to be looking almost entirely at the B field, the integrated signal, because it's a strong conductor in late time, so it's really going to show up much better in the integrated data. And this is what the section looks like. We've got the altimeter, the magnetic, dBz by dt, it's there, and if I were to expand the scale of that, you'd see it is there in the late time at dB by dt. That first profile, by the way, we looked at was dB by dt. But it's a lot more obvious in the B field, which is the lighter green in the middle. And a little hard to see, we can trace it out. That's basically the anomaly shape there in the latest time channels. And as well, shows up really nicely in differential connectivity. So here's 3 lines over it. I mean, that's the other thing. All geophysicists like to see it repeat, and certainly we're seeing the same thing with the same connectivities in that on multiple lines, so that gives us confidence. And the deposit's big enough that it's going to be underneath several lines. And you can see I've drawn on the 3 picotesla noise, about the noise envelope. Maybe that's a little bit pessimistic. It's lower in a lot of places. And then, again, you prepared this. I don't know why I put late on the left and early on the bottom right. I would have gone the other way around. But basically, starting from the early time in the bottom right, you can see you've got a whole zone of conductivity through there. And when you get up to about channel 19 or 24, we've got more concentrated conductivity on top of the conductors. By channel 29, it's still concentrated, but it's getting pretty noisy. We pretty much run out of signal there. So that's actually the amplitude. So we're getting the strongest signal over it. And we see the same thing when we do the conductivity calculation. Shows the 2 separate zones. And really shows in late time it's cleaned up the background some too, so you see more discrete bodies. So that's channel 29 looks like, and we're right down close to the noise level there. The whole thing here, we were working pretty close to our noise level, but that's just a matter of working a little more with the data. Here's what the differential connectivity sections look like over it, so I've sort of cartooned on where the deposit is there on the center line. Although you got to remember it does extend over several lines. I haven't tried to draw it in 3D. That's just basically roughly where it is. And we've got nice connectivity on all of our lines and a little better signal strength of the center. That's it there. And that's about the depth of it. And you can see for something as approximate as the differential, it doesn't even do a bad job of getting the depth more or less in the right place. Now this is the south bullseye anomaly. This is the one further to the south. Similar sort of response, maybe even a little bigger on the BZ there, and a good response of differential connectivity as well on the right there, just where the word cond is a power line response. There's power lines all through the area. This is what the south one looks like. So yeah, a little better, not a lot, but a little better. Very distinct though. It's there in all the channels. It holds up in the K curve. So, and here's what the south one looks like. There's, I think, only 1 drill hole into it. At least there was when we were doing this. So we don't have much geological information about it. Would I dare to say that looks like it's dipping to the north? That would be in agreement with the other geology in the area. But yeah, might be working. I'll have to find out. Depends whether I'm selling it or not, whether I'd say I believe it. And we did the 15 hertz, as I mentioned. So we've got 15 hertz base figure. We went with the 10 millisecond pulse just to see what we could get out of it. You've got tons of off time, so you're not losing significant off time by broadening the pulse. Same sort of power, a little bit less power. And there's a trade-off here between how many times you're pulsing and the width of the pulse, how much power you end up drawing. And it looks something like this. So there's the EM profile on the top, the connectivity section. Connectivity section looks good. There's certainly more noise in that data than there was in the earlier data. And it turns out, to our pleasant surprise, the noise is exactly what you would have estimated, about 1.4 times higher that you would expect from having half as many samples in there. Most 15 hertz experiments in the past have been a lot noisier than sort of the predicted theory. And that's just the next line over the south bullseye. So good one, good response again. You know, it hangs up there. It's in the noise, but it hangs up there in the late time. There's also a power line sitting right on top of it, so that affects the data. it's important to recognize that the power line is almost always a conductor. There might be 60 hertz noise, or there might not be from a power line, but the power line itself has a grounded wire on it normally, and that's a conductor. So you'll usually see it in your data. Doesn't mean there's anything wrong. That's not interference, it's a conductor, just a man-made one. And this is a comparison of the 30 hertz and the 15 hertz. So we're seeing similar signal levels, a little more noise in the 15 hertz, but still a good response. The width in that is repeatable. And then the connectivity sections, the differential connectivity sections. I think we plotted at 15 hertz a little deeper because we've got a few more off-time channels, but we do run out of signal. So 1.6 million 10 millisecond pulse worked well, detected the Lalor deposit. The noise level is exactly what we would have predicted, which is good news. Not a lot of signal increase, as I mentioned. Well, our last time channel at 6 milliseconds is about 10 milliseconds after the pulse, but 1 millisecond after the pulse, we've already passed our peak signal. And by the time we got to that last channel of the 30 hertz, there wasn't much secondary field left. So adding another 16 milliseconds of off time in 15 hertz really didn't give us anything that useful in the results. And so 15 hertz, people think, gets you deeper, gets you stronger conductors. It does, with really strong conductors that still have signal, or in really conductive ground, but in a lot of Canadian conditions, it's not going to give you much because you're just going to be sort of sampling dead time. So if you have a really strong conductor, you may do a better job of actually characterizing the decay when it gets to the late stage decay. Now, so then we went on and did a bunch of modeling. And we did two types of models. We did discrete plate models, which use plate, if you know that. It's uses a plate type model in free space. It's very fast and convenient to use. And we also use Leroy Air from the Amira modeling program. And that one works. It's a conductive host. And it's much more complex. You can have plate interaction, all kinds of things, but that sort of thing slows it down, especially when we got this pancake stack of plates. It defines the geometry. This is why I like discrete plate models. It defines the geometry of the conductor fairly well. Better for targeting it with a drill, better for comparing it to geology if you have it, and also works to define multiple zones, or it can. However, it seems a good match to a plate-like conductor, which isn't always the case geologically, and I'm a little uncomfortable with it for multiple plates and how they're interacting, how well it's working, and they really slow down when you have multiple plates. The other one we did was the arbitrary or finite element models. We had Dukun Yang at UBC run that for us on the UBC code. The nice thing about it is there's minimal model dependence. So you just plug it in, set it up right, and close your eyes and let it run. So it's in that respect relatively hands-off. But I have difficulty with it because there's no geometric information. You don't get dip out of it. You get a somewhat conductive blob. Here's what the plate modeling looked like. We did it in our own system there using, I think I used mostly plate just for speed, and then Leroy sometimes. Started out with, I knew what the plates were like, so I started with things close to them, but I had to make them a little bigger than than what's sort of known from the geology to get the type of signal. So these are some of the zones that are down there, and then the others I just lumped together. It is difficult to model these things because one is copper rich, another one is zinc rich, so you're really getting into uncertainty trying to determine what the connectivity of each of these things is going to be. Modeled the power line on top of it, really just to visually remove the bump near surface. And I also found I had to add more connectivity in the form I just put a plate there, which may represent the stock work. It may represent other things which aren't being reported by the geologist. As I showed you in the map view, there is sort of a conductive band through here, so there's more than just the economic bodies there. So it's a pretty good fit. What I'm showing here is dB by dt and B field, and the blue line is the field data, and the red dots are the model. And so not a bad fit for decay or for amplitude, but you can see in dB by dt it's decaying too fast, and in B field it's decaying too slowly, and it's not a pure exponential, the decay that we see out of our conductor. That's really not a big surprise because running a conflict between the model and between reality. Real conductors aren't smooth plates. They interact with each other. They've got fuzzy edges that and various thicknesses, so they won't go to a pure exponential decay. Usually you just try and get it as close as you can. And just to throw the geology back on there, we've got this intense hydrothermal alteration underneath, which is not going to have an exponential decay because it's not plate-like. So we're going to have a really mixed decay. So it worked. It's not really good. We've got the amplitudes fairly good. I don't know how much better you could do. And onto the 3D inversion. He set up a 3 by 3 kilometer fine mesh in the center there, and then around the whole thing, a 14 by 14 kilometer coarse mesh. Rotated the whole thing 42 degrees, so you'll see in some of these models that north ended up getting turned a bit. That's what the mesh looks like. So now we've rotated the whole thing. And this is what the results look like, and what I've done is I've stripped away everything that's less conductive than 3 millisiemens per meter, so I'm just showing the conductive material in the center. And his mesh didn't extend to that conductive, it was off the northeast. Zoom in a little closer, so we got the two bodies, the south bullseye on the bottom, or to the south, and the Lalor Lake to the north, as well as some connectivity further to the north that I didn't have an explanation for, although I gave this talk at the BCGS, and somebody there said, yeah, we do have some connectivity that we see up there. Now you can take the whole thing and slice it at 550 meters, and that's what we see. So we've sort of zoomed down, got rid of that near surface stuff to the north, and again, a good match. They're both there. If I take this now and look from that angle and turn the whole thing, so I'm basically looking to the northwest, that's what it looks like. So looking through past the south bullseye to the Lalor Lake deposit, looks like that. And so we see the two. We certainly see that same dip that I saw in the differential connectivity. We see that dip as well in the south bullseye. So they're agreeing with each other, which is nice. I can take it, slice it there. So I'm slicing through the Lalor Lake itself, and I get something like that. You can see behind Lalor that connectivity that comes to the surface. If I take it now and slice it at 550 meters, that's sort of isolating where the inversion thinks the conductor is for Lalor Lake. And that's not too bad a match to where it is. Really imaginative. You can actually claim to see the dip down through here. I'll leave that to your imagination. So the results can be modeled to match the geology, sort of. 3D, we get a blob in the right place, which is good. Plate models, we get something pretty close, little differences in the decay. Both of them show some excessive conductivity in the area beyond the geological description I have, which is just out of the public material. So that could be the stock work. It could be graphite and pyrite through there. As I said, we know we've got a broad zone of conductivity through there. The original modeling also underestimated the signal, which is interesting. My models beforehand underestimated the signal, and I had a hard time with the inversions matching the amount of signal I was getting, which probably suggests the same thing. There's other conductive stuff there than our strict geological model. And there's a lot of work could still be done to refine the plate models, including the plate interaction, the stock work, host geology, the connectivity that's in there. Pretty quick. So results show the HELITEM with 30 hertz was able to detect the Lalor Lake deposit, did it quite well. The B field Z amplitude or Z data showed very low amplitude, long wavelength anomalies over the deposit. I could add there the X component didn't show very much at all. It doesn't couple as well. You're looking for a crossover. It just wasn't that useful. These are pretty flat line things. The 15 hertz worked well, worked pretty much as the theory would predict, which is actually a good thing because a lot of 15 hertz tests in the past didn't even match up to the theory. It is challenging. It's a deep target with a low amplitude response. Survey areas infested with culture by Canadian standards, not as bad as it would be in the U.S., but there are power lines, there's mining in the area, and certainly more modeling will be interesting. I'd like to thank Hud Bay. They give us permission to fly the survey and some support along the way and some technical information. Dukun Yang at UBC, who actually did the 3D inversion, did a nice job of it, and Yu Chen has my co-author, but in our office he did most of the processing and spent a lot of time trying to find the sort of the best result out of the processing. Thank you.
Thank you, Greg. Thank you very much. If we have any questions, and if there's some people online that have some questions, please type them out, and Elizabeth will read them out. But any questions from the audience here?
Yep.
So I think that's pretty impressive for a helicopter system. And how come you guys aren't up there flying around all over the place now? Or are you?
Well, I won't tell you how much we are, but I don't think anybody's real busy right now, are they? No, it worked. Why aren't we doing more? I said, if that's our clients and our salespeople, that. I mean, it worked well on a deep target. It's an obvious target for a time domain EM, being a pretty strong conductor and resistive host. So,
question 2, you said there's one drill hole in that bullseye, that south bullseye.
that's my understanding. Yes.
Any info about the drill results?
I didn't receive any.
There's more like half a dozen drill holes in it, and it's a string of copper.
So is it economic?
We're not building one. We're building one.
Sorry, I'll repeat that for him. You said there's half a dozen drill holes and it's stringer zones? And
Yeah, it's stringer copper pipe.
Stringer copper pyrite. Okay, so all the geology I presented was from the public files. I've tried to hunt out more yet.
What was your cell size for your 3D model?
The cell size for 3D models was 3 kilometers in the center part. That couldn't have been. No, it's a 3D block, and I just looking at it. Oops. There's a 3 kilometer square, and then you can see the cell size within that. I can't see it from here. I can figure it out, give it a bit of time, but it's in the order of 50 meters, I think.
Any depth to the chisel blade target? Like when you had the cross section, you had it down at 550 meters as well?
It was about the same depth. Yeah, I haven't tried to refine it. Flat-lying deposit like that's going to be hard to get an accurate depth off the EM. And I didn't do plate models on that south bullseye.
And just one last thing, when you put that plate that's in the hanging wall, what made you put it as a horizontal plate to explain the excess conductivity?
Just to get a broad, wide conductive zone. That's why I should repeat the question, why did I use a horizontal plate for that? To get a broad zone, and because it is conformal with the rest of the geology we're seeing there. Would have been a vertical plate, of course, would have a low in the middle of it in the Z component, which I wasn't seeing in the data.
So that the south bullseye, that you said that was discovered by large niche down time domain EMs.
Both were discovered by large soup.
Dennis Woods that did that stuff?
No, I don't think so.
Alan Bell's with Hyundai.
I have a question about that mystery conductor in the hanging wall. How much of that response did that mystery conductor explain? I mean, the problem is we have multiple stacked plates. Usually the top guy explains most of the response. Like the top
Yeah, it's a lot less conductive. You see that's about 4 Siemens compared to about 100 Siemens for the other, so that mystery plate was there just to give amplitude in the early times, more so in the late time.
But I mean, it's still pretty large. I mean, that time would be pretty big too, right?
Yeah, it would, but nothing compared to these 100 Siemens conductors.
Well, no, it's time constant and then the plate size as well. This is stuff.
Yeah, but the
So
plate,
that's kind of large.
it's dependent mostly on the minimum size of the plate, which is only 400 meters compared to 800 meters minimum size for the others. So 8 times 100 compared to 4 times 400 would be the relative decay constant, sort of. So it's a lot less conductive, a lot faster decay, and that was just sort of bulking up some of the earlier time. It probably, based on geology, should be underneath it. And that would be more like the stock work then.
That's a big comment about that.
They've seen it. I don't think it's,
Yeah.
no, it's, as far as I know, as far as I'm concerned, it's just stuck in there to get some signal in the mid channels that I wasn't seeing. And I'm not pretending it's accurate. Like I say, if I was sticking strictly to geology, I should put it underneath and assume it's the stock work. But I don't even know what depth that sort of broad conductivity you see through the whole area, if that's at the same horizon. I assume it is, but. Bert?
It's very impressive for the deep target. Then you do your modeling studies. You come up with some rule of thumb for the model you did, the extent of your plate, and the width of the plate. Then would you lose the signal if you have to reduce the width?
So,
Okay, for your plate model, you're using length
yeah,
and width.
yes.
And then you make it narrow. At what point would you essentially say at the top?
Yeah. So the question was basically, well, I guess, really what's the relative importance of width and length, and where do you start to lose it? I don't have a hard number on that, but it still sort of comes back to my preferred or favorite rule of thumb, which means when it starts getting narrower than it is deep, like so when the minimum dimension is less than the depth, you're really going to start losing amplitude fast. And then as Bob alluded to, also you cut the width in half and the decay constant is going to drop quite a bit too. So yeah, that's where I would drop it. These numbers, I used the known size of the plates there. I'd really, instead of putting in the mystery plate, what I could have done, except I don't have geological information, is make zone 10 and 20 much wider, and I would have got more signal out of the thing, but that doesn't fit the known geology. So it's, you know, this wasn't necessarily an exercise in trying to get it exactly drill. It was just to see how well it does conform to what we know of the geology.
My problem with this is that you have a bump there, but you can't model that with only a deep conductor of the proper size.
No, I can't. Not with these ones known here. I could not get enough response from the small stack of known conductors, although, as I said, I don't have a really good conductance on each of them because they're quite variable in their mineral content. So I don't have a really good handle on it. I do have a good handle on the size, and I could not get the signal I'm seeing from those conductors, either in my modeling beforehand or my modeling on these data, which says, yeah, there's something else conductive down there. I stuck a mystery plate in the easiest place. If anybody wants to pay me to spend another week or two on this, I'd be happy to work on it further, but this was done on my own time and our own dime. So, no, it's why I call it mystery. I'm not seeing enough signal from the known conductors to explain what we're seeing in the data. Any other questions? Thank you, but no. Got all my anti-cold drugs in me. I wouldn't want to be drifting off when I'm driving home.
Well, actually, sorry. Did you have a word model to your inversion to see how well that did?
That's, sorry, that's what the red is. The green is the field EM, and the red is the Ford model.
No, none of the play for the 3D.
Oh, no, from the UBC 3D. No, we didn't try to, well, I didn't get an output. I presume their program output, but it's a good question. I should ask Duke and Yang if he has the Ford model data from that.
Have you duplicated this system? Like, is this now your go-to system based on these test results, or are you continually flying with the standard HELITEM configuration?
Except for the 6 millisecond pulse, this was our standard HELITEM, the 30 hertz, which I think we've got another job with 6 milliseconds where it was appropriate. So yeah, it is our standard system. We normally use 4 millisecond pulse because it's a little bit broader application, but 6 milliseconds is fairly straightforward to do.
Well, thank you, Greg. Thanks again for coming out and being so sick. Being a champ. Thank you.